Yes, thank you so much. Entitled X-ray Computed Tomography and an Erosion Algorithm for a Rapid Defect Detection. Please come back. No.
Thank you. I'll just click, it's easier. Hi, my name is Aaron. I'm a PhD student at UCL, where we use a lot of X-ray tomography, and this talk is going to be on battery materials. So maybe you'll know, maybe you don't, so I'm going to start from the bottom and then walk through what kind of stuff we've done. So the motivation for this work is that battery materials crack. So these images were taken, both took 24 hours to acquire, and you can see cracking in both of the samples. So the two kind of issues we wanted to solve is number one, 24 hours to get 50 particles isn't great, and then number two is they're both cracked, but how cracked are they? Can we quantify that and reduce the time to scan while doing so? So I'm going to quickly talk through the algorithm that we've kind of come up with, then an ex situ study, the CT, and then an in situ study that we've recently completed. I think it's always important to think about why we're here, what we're doing. And batteries at the minute are kind of rising in popularity due to their potential for lithium-ion batteries, being EVs. So if we have an EV, we can decarbonise our grid and store energy in our batteries, or we can put them in our vehicles and like the emissions in our cities go down to cleaner air for everyone. So a lithium-ion battery works by moving the lithium ions from a cathode to an anode and vice versa. So when your battery is fully discharged and dead, all your lithium ions are in the cathode, which is on the right-hand side, and then when you plug it in and charge it, they move over to the anode, and then when you discharge it, they go back the other way. And doing this doesn't just cause cracking in our particles, it causes a whole range of elimination mechanisms, some of which are coupled together, as you can see from this image on the left. So we have particle fracture down here, and this can lead to new surfaces being exposed. Because our cells are wet, when these surfaces are exposed, the electrolyte seeps in, which causes side reaction, which causes a loss of lithium, and eventually you get kind of battery failure. So we have two different types of cracking. We have intergranular or intragranular. Intergranular is much bigger, and that's kind of what the focus of this work is. So there are currently in battery research three different ways that we can detect and diagnose cracks. The first is FIB-SEM, which gives us really good resolution and some really nice images. However, it's destructive and takes absolutely ages to do, so it's not particularly useful for large data sets. Then we have nano-CT, like the images I showed at the beginning. And this is pretty good resolution, you can still see the cracks, but it's non-destructive, which is nice, but it's still time-consuming, so an image can take 24 hours to 48 hours. Or we have micro-CT, which the resolution is good but not great, so you might be able to see some cracks, but you might have to infer the presence of others. It's non-destructive and it's fairly rapid, so some of the scans I'm going to present, some can be done in the lab in 4 hours, or even quicker if you get to synchrotron, so it's pretty quick, and you can get thousands of particles per day rather than your 50 or so. So quick little background, so my lab can do these three CT machines, so we can do anything from nanometers up to microns to like a whole phone, so you can do like a nice big scale of imaging. And CT works by you shine an X-ray at a sample, and then that's called a projection. You expose that for a certain length of time, then you rotate it, do that again, get hundreds to thousands of projections, then reconstruct it into a nice 3D volume. So the first thing we thought to do was to look at our particles and pick them out by hand and look at the intensity through them. So if you look at the two lines on the right, this is their kind of intensity. And you can see in the middle where there's a void, this intensity drops. So we can kind of infer that if there's a drop in intensity somewhere, there's either a void or a crack. Doing this by hand is really time consuming and not very productive. So we came up with an algorithm that would do this automatically, do it a bit smarter. So instead of looking at line scans through a particle, we look at erosion through the particle to get kind of the whole volume of our particles. So one way we can use this is operating our batteries in different ways. So along the top is batteries that have been charged once and then opened. So different voltages is basically how much lithium you remove from the electrode. And as you can see, hopefully you can see, there are cracks in all the particles along the top, and then when you put the lithium back in, these cracks close up. But again, these images take a long time. So the algorithm we've used has helped us quantify this and see this on a much larger scale. So what we've done is, on the top is the intensity through an average particle in the data set. And we can see that all of the charged particles, which are the filled-in spheres, have a lower intensity on average compared to the discharge, which is the hollow, and then the pristine, which has never been in the battery, has the highest intensity. So we can see that there are cracks forming, even if we can't visually see the cracks, and we can kind of calculate how bad the damage is compared to pristine. And this is for the biggest particles, so we can also do that for all of our particle sizes. So this is a percentage of particles that contain a defect. And we can see that as the particle size is bigger, more particles have a defect, and all of them have more particle defects than the pristine. So this is a nice way to compare, if you have something that you've never used, if you cycle it a little bit, how does its damage change over time? And then if you try and undo that damage, how far can you go? One of the big questions you might have is, could the damage be caused by fabrication of your materials rather than this cycling behaviour? So we've done some in-situ work. We've taken the exact same electrode, taken it to a synchrotron, and imaged it at different points in its life. And again, we've done the same kind of normalised intensity tracking. And what we see is that the pristine and the fully discharged, with the top two lines, show the least amount of damage, and then the stuff that's taken to the high voltage or on its way back down has this kind of normalised intensity towards towards the core. And as you go towards the core in battery materials, that's where the cracks start, and then they kind of come out. So we can see that if you've got a lower intensity in the middle, it's likely that that's a crack, and that's kind of across all the particles. And then something that's really nice that we can do with this in-situ work is track a single particle through its life. So here we have exactly the same particle, and this is in its pristine state. When it's never been in the battery, it's just kind of chilling. And then as we take it up to higher and higher voltages and we remove more and more lithium, we can see its intensity in the core goes down. So this lower intensity down to 0.98 is kind of indicating that there's cracks or defects in the center. And then as we put the lithium back into the particle and discharge the battery, we can see that those cracks are starting to close up and kind of self-heal. So we've only done one charge and one discharge. So our kind of goal is to do this many times to see if these cracks exist for a long period of time, or if they kind of turn up and then disappear and don't come back again. But we've mapped the integrity of thousands of particles internally. We've both done lab scale and synchrotron work for ex situ stuff and in situ. Hopefully this method is material agnostic, so one of my kind of reasons to come here is I want to work with people who know a lot more about fracture than I do. I'm kind of like a battery or X-ray guy looking at fracture. Hopefully some of you are fracture people who want to apply what you know to battery materials, or we can apply this method to your materials to quantify how bad the damage is. So we'd love to collaborate, and this is just like thanks to lots of different people in my group who helped out with this work.
Dr. Wade, for your interesting presentation. Questions for Dr. Aaron? I know practically nothing about your research.
It's okay,
but
I know nothing about fracture.
The environment temperature eventually could it control the erosion of the battery during discharge process?
Yeah, so we try and keep the batteries at the same temperature throughout the process.
This is what for example, in critical application computers, to develop one more gadget to keep the battery at a stable temperature.
Yeah, so one of the biggest things that kills a battery is temperature hotspots.
Some kind of dissipation.
Yeah, so like in an electric vehicle, they have cooling running through the battery to keep it at constant temperature. So I don't know if you can do that on your phone, but trying to not get it too hot can definitely extend it and stop it dying sooner.
No questions? Thank you so
Cool.
much.
Thank you.
Next work is entitled 3D Tools for Building